Today's engineering topic is rankine cycle. So what are we waiting for? Let's start this right away. Rankine cycle was named after Scottish polymath and Glasgow University professor William John Macron Rankine. It is a vapor power cycle. For a little definition, power cycle is a cycle which uses heat to generate work, and since it's a vapor cycle, it uses the vapor phase, or in this case, steam, to rotate the blades of the turbine. It actually utilizes the heat energy contained in coal, oil, or natural gas, and then converts it into mechanical energy and eventually electrical energy, which of course provides electricity in our city and in our homes. One of the best definitions for this cycle is that it closely describes the process of steam turbine systems and is derived from the Carnot cycle, the most efficient thermodynamic cycle, which tells us that power is dependent on the temperature difference between a heat source and cold source. The higher the difference, the more mechanical power can be efficiently extracted out of heat energy. So now, let's talk about the variants or the types of Rankine cycle. We have a reheat Rankine cycle. It is a cycle which we introduce the exhausted steam back into the boiler to reheat it. We also have a regenerative Rankine cycle. We bleed apart the steam into heat exchangers to preheat the feed water before entering the boiler. There is also an organic Rankine cycle. It uses an organic high molecular mass fluid with the boiling point occurring at lower temperature than the water-steam phase change. A supercritical Rankine cycle is also one of the types. Just like reheat and regenerative Rankine cycle, water is the working fluid, but it is operated at above its critical pressure. So, those are the types of Rankine cycle, but here, on this video, we will only discuss the most basic and fundamental of the cycle, the ideal Rankine cycle. We must be aware first that this operates slightly different than the real Rankine cycle. This is a reversible cycle. Common sources of irreversibilities are neglected, such as frictional pressure drops and undesired heat transfer with the surroundings, a constant pressure or isobaric process, and constant entropy or isentropic process are used for the equipments involved in the cycle. The working fluid is water, and it will undergo a closed loop and will be reused constantly. So why do we use water as the working fluid? Well, simply because it is not toxic, not reactive, highly abundant, low cost, and good thermodynamic properties. To make a Rankine cycle, we need 4 processes. Process 1 to 2 for the boiler, process 2 to 3 for the turbine, process 3 to 4 for the condenser, and finally process 4 to 1 for the pump. And that is what we are going to discuss for the next part. Okay, so let's get this started. For process 1 to 2 boiler, these are the things that we need to remember. Since boiler is a heat exchanger equipment, a heat is added into the boiler through a fuel, which may be coal, oil, or natural gas. Here, water is converted into steam or superheated steam. This is an isobaric process or a constant pressure process. The temperature and entropy for this process increases. And we can solve the heat addition by using the formula heat added equals fluid energy out minus fluid energy in, or enthalpy out minus enthalpy in for the boiler. Note that this equation is formed by using a mass and energy rate balance for a control volume at steady state, neglecting pressure drop. So those are the important things that we should remember with understanding the boiler process. Now, steam can be used in the next process, which is the process 2 to 3 turbine. Turbine is a work generator equipment. It contains series of stages or set of stationary and moving blades to perform its function. By using the steam, work is generated through the expansion of vapor, which may then be converted into electricity through generator. Compared to the previous process, here, since we have an equipment that involves work, isentropic process or constant entropy process is assumed. Yes, it is assumed because in real world, there is no such thing as ideal. On this process, the temperature and pressure decreases. And the formula for the work is fluid energy in minus fluid energy out, or the enthalpy 2 minus enthalpy 3. Note that equation is formed by using a mass and energy rate balance for a controlled volume at steady state, neglecting heat transfer with the surroundings. Steam is now already exhausted, and so we need to take it back again to the boiler, but there is no pump that can pump steam, so we need to convert it first into water through condensation. So this is where our next process comes in. Process 3 to 4 condenser. In order to condense the steam, a heat rejection must occur. Most of the power plants utilize the seawater as a cooling medium to cool down and condense the steam. Condenser consists of tubes to accommodate the heat transfer of steam and cooling water, where cooling water is in a separate stream. This is a heat exchange equipment, so we assume that this is an isobaric process or constant pressure process. The entropy decreases, and the quality of the fluid changes until it reaches a saturated liquid state. So from steam to liquid. The equation is heat rejected equals fluid energy in minus fluid energy out, or enthalpy 3 minus enthalpy 4. Note again that this equation is formed by using a mass and energy rate balance for a controlled volume at steady state, neglecting pressure drop. Last process is process 4 to 1 pump. Pump's main purpose is to convey and introduce back the condensed steam into the boiler. Here, work is needed. That means work is negative. Some plants name this pump as boiler feed pump, and it can be either steam driven or electric motor driven. Again, since this is a work involved equipment, we assume that this is an isentropic process or constant entropy process. The temperature slightly increases, and the fluid is in a subcold region in the TS diagram. The formula for the pump is work equals fluid energy out minus fluid energy in, or enthalpy 1 minus enthalpy 4. Fluid energy out or enthalpy out is greater than the enthalpy in, as the pump have imparted energy to the fluid. Note again that equation is formed by using a mass and energy rate balance for a controlled volume at steady state, neglecting heat transfer with the surroundings. And one more important thing, please remember that the pump has the highest pressure in the whole cycle. Okay, so let's have a recap. Starting from the boiler, we convert the liquid water into steam. Introduce it into the turbine to generate work, and then we condense it into the condenser and pump the liquid water back to the boiler through a high pressure pump. So that's it. Engineering is a fun thing, and it always has been. See you again for our other easy and fun engineering topics. Is engineering topics made easy and fun for you.